Okay. As we have discussed earlier, the major reaction the alkyl halides undergo are the nucleophilic substitution reactions. Okay, these nucleophilic substitution reactions are of two types, SN1 and SN2. S stands for the substitution and stands for the nucleophilic. 1 and 2 have their own significance. 1 is the unimolecular reaction and 2 is the bimolecular reaction. So let's start with the SN2 reaction, right? The reaction which is written over here, okay, this is SN2 reaction. Okay. Here you see methyl bromide is the substrate and iodide the ion is the nucleophile. Iodide ion is the nucleophile. So when methyl bromide is attacked by the nucleophile, it gives the methyl iodide and bromide. Okay, or you can understand as the OH ion. If it is OH ion, okay, so then we get here methyl alcohol. Okay, so OH ion is the attacking nucleophile and bromide ion is the leaving nucleophile. Okay, this particular equation example is given in your NCERT book. That's why I have written here OH minus ions. This is the attacking nucleophile and this is the leaving nucleophile. Now come to the mechanism. What happens when this attacking nucleophile OH is attacking to the carbon atom which is providing it the nucleophilic site, okay, then and bromine is leaving it. Okay, bromine is leaving it. You can see bromine being the more electronegative than carbon atom moves away with its electron. Moves away here means right now it has not left completely. Okay, it has started leaving and OH has started attacking and it reaches to the point where carbon atom is attached to the 5 other elements, 5 other atoms. Okay, 3 hydrogen which were already there, 1 bromine, another OH ion. If we write here OH ion and another one is the OH ion, we can see that bromine is leaving. That's why it is shown with the broken or discontinuous bond, and at the same time the OH is getting attached here through the broken bond. And this particular state when the carbon atom is attached to the 5 other carbon atom is known as transition state, which is highly energetic as carbon is attached to the 5 other atoms. Highly energetic, very unstable, and after this it gives the final product as the methyl iodide, as you can see, or if it is the OH ion, it is OCH3 along with the left nucleophile. Okay, so this way we get the product. One of the method of preparation of alcohol from the alkyl halide, or one of the method of preparation of the iodide derivative of alkanes from the bromo derivative. It could be chloro derivative also. Okay, is that clear? So it is SN2. It is SN2, right? Nucleophilic substitution reaction, bimolecular nucleophilic substitution reaction. This reaction takes place in one step. This SN2 is taking place in one step, and in this one step the two reactants, two molecules are affecting the rate of reaction. That means in the rate determining step, two reactions, the two molecules are present, therefore it is bimolecular. It is bimolecular or second order reaction. Bimolecular or second order reaction, as in the rate determining step there are two molecules, two reactants which are affecting the rate of reaction. Okay. Then we move to the next point. Okay, then we move to the next point. What it is? See, okay, in the SN2 reactions, okay, the electrophile the nucleophile, the attacking nucleophile is coming from the end, from the side opposite to the leaving nucleophile, okay. The exit gate of the leaving nucleophile and the entry gate of the attacking nucleophile is different, okay. That's why the position of the attachment of the incoming nucleophile and outgoing nucleophile is different. This point we discuss later under the stereochemical aspect. Now see here, the OH ion or the attacking nucleophile which is attacking to carbon, it has to reach to carbon, making the way through the other groups present here. So smaller the group, less is the obstacle to reach to the carbon, which is the site of the attack, okay. So less the hindrance, less the steric hindrance, less is the obstacle, this obstacle technically known as steric hindrance, okay. Better is the reactivity. Smaller the group, less is the hindrance, better is the reactivity. Therefore the methyl group results into the most favorable condition for SN2 mechanism, followed by the primary carbon atom, the primary alkyl group, which represents here CH2R, okay. Smaller the R group, less is the hindrance. Secondary alkyl group provides more hindrance. The tertiary almost nil probability for the SN2 mechanism, because here the nucleophile has almost no way to reach to the carbon atom. So this represents the rate of the SN2 mechanism, almost nil for the tertiary, better secondary, even better primary, and the best with the methyl, which provides the least hindrance as the carbon is containing the small hydrogen atoms, okay. Now we come to the stereochemical aspect of this reaction, okay. Then so sorry, before that we discuss the graph. Here you can see the reactant, okay, methyl bromide and the attacking nucleophile hydroxide ion, okay. When they react, okay, this is the energy of the reaction, okay. Additional energy required is the energy of activation energy. When they get this with this energy, they reach to the transition state, which is highly energetic and short lived, and after that it breaks into the product, giving the alcohol and the leaving nucleophile and corresponding product, okay. This is the graphical presentation, okay. Then we come to the stereochemical aspect. Just now we discussed that the attacking nucleophile comes and attaches to the back side of the leaving nucleophilic site, okay, and it results into the product known as inverted product, okay. And this phenomena is known as inversion. Inversion means the site of the leaving nucleophile and the site of the attachment of attacking nucleophile is different, it is inverted, okay. Now if we go to the stereochemical aspect, we have to understand few of the terms. So first term which we should know is the optical activity. We should know the optical activity. What is optical activity? It is the term related to optical isomerism, which is one of the stereoisomerism. What is optical isomerism? Optical isomerism is related to the behavior of the compounds towards the plane polarized light, Now what is plane polarized light? Okay, plane polarized light is the light the vibrations of which are only in one direction. Please come to this figure Okay, here we can see the vibrations of the light in all the directions. When it is passed through the filter, for example nickel prism, then we can see the vibrations in one direction only. So this light is known as the plane polarized light. This light, when passed through the optically active compound, it rotates the light either in the clockwise direction or in the anti-clockwise direction, So this behavior is known as optically active behavior. The rotation of plane polarized light by the compound is known as its optically active behavior. Now if the compound rotates the plane polarized light towards a clockwise direction, it is known as dextrorotatory. And when it does in the anti-clockwise direction, it is known as levorotatory. It is represented by small d or positive sign, it is by small l or the negative sign. Okay, so I hope you are clear with these terms. Okay, then what happens? We use the term optically active compound. Okay, so the compound should be optically active to show the optical behavior. What should be the compound? Compound should be the optically active. Okay, not to be optically active, what it should have? To be optically active, the compound should have the chiral carbon atom, or it should have asymmetric carbon atom. Now what is asymmetric carbon atom? Asymmetric carbon atom is the carbon atom which has all the 4 valencies fulfilled by 4 different atoms or group of atoms. So the carbon atom having all the valencies fulfilled by the 4 different atoms or 4 different group is known as the asymmetric or chiral carbon atom. Right, you can see the figure here. Okay, here this is carbon atom and these all 4 groups are different. All these 4 groups which are satisfying its valency are different from each other. So it represents the chirality of the carbon atom. Here you can see the plane mirror. Okay, plane mirror. So when these compounds which are having the chiral carbon atom or asymmetric center are placed in front of plane mirror, they give the image which cannot be superimposed over each other. So such images which cannot be superimposed over each other are known as enantiomers. These are known as enantiomers, and the best example of this is a pair of hands. Okay, when these hands, when we keep side by side, it gives us the mirror image, and they cannot be overlapped over each other. They cannot cover each other, and here covering means each other just by sliding over each other, not by rotating, not by fitting anyhow. So our hands represent the perfect example of the enantiomers of the mirror image. Okay, so the compounds which are optically active, they have the chiral carbon atom only. Even one is sufficient, but they should have the chirality. Okay, so when we are talking about the SN2 reactions, we see that we are getting the inverted product. If the leaving nucleophile is leaving from here, the attacking is coming as and getting attached here. Okay, and if the our substrate alkyl halide is containing the chiral carbon atom, and alkyl halide is containing the chiral carbon atom, or it is optically active, then the product obtained will have the different behavior from the reactant from the alkyl halide, which is the substrate. If that alkyl halide is levorotatory, then the product will be dextrorotatory, and if it is dextrorotatory, then the product will be the levorotatory. This is the stereochemical aspect of the nucleophilic substitution reaction. So in SN2, which takes place in one step, which is second order reaction, which is bimolecular reaction, it results into inversion. And if it is optically active alkyl halide, the product obtained will be of opposite optical nature. Its optical activity will be different. Okay, I hope it is clear. Okay, then we move to another, the SN1 mechanism. Okay, now when we are moving to SN1 mechanism, what do we observe? See, in SN1 mechanism, in the first step, which is the slow step, the nucleophile, the leaving nucleophile is going. Okay, this is the first step. Nothing else is happening. The leaving nucleophile is leaving. Now this is carbon atom. Okay, and attached to it is the halogen, carbon halogen. The difference in electronegativity, that's why the halogen leaves with both the electrons, leaving behind the positive charge. The formation of cation, the formation of carbocation takes place. Okay, the formation of carbocation takes place. So this carbocation is planar in nature. So in the first step, formation of carbocation takes place, and this step is the rate determining step. When the reaction is taking place in multi steps, the slowest step is the rate determining step. So in the rate determining step, formation of carbocation takes place, which is planar structure. Now the attacking nucleophile has both the probabilities. It can affect from the upper direction or from the lower side. From both the sides, it has the chance, it has the probability to attack. So if it is attacking from the same side, from the side of leaving the nucleophile, then the product formed is with the retention. But if the attacking nucleophile is attacking from the opposite direction, then the product formed is with the inversion. So here both the probabilities are there, inversion as well as retention. Okay, inversion as well as retention, right? So if we go for its stereochemical aspects, you are clear with the terms. Okay, stereochemical aspects, that means the carbon atom, okay, the carbocation, the carbon atom of the alkyl halide, if its four valencies are fulfilled by four different groups, then it is optically active. So when it is optically active, we apply here the stereochemical aspect. So here, if the attack is from the same direction of the from where the leaving group has left, then it will be resulting into the retention, and if it is from the opposite direction, it will result into the inversion. That means if the alkyl halide is dextrorotatory, the 50% will result into the retention, okay, and the 50% will result into the inversion. So they will cancel out each other, and the resultant product will not be optically active. Because 50% of the optical nature is retained and 50% of optical nature has inverted, and they cancel each other, resulting into the optically inactive product which is known as racemic mixture, Now children, remember here that if it is totally cancelled, it is racemic mixture. If it is partially cancelled, then it will result into the optical activity depending upon this, that which one is exceeding. So accordingly it will be. As we have seen that here the carbocation formation is taking place, and stability of carbocation decides what will be the mechanism formed. Okay, and we have already studied in grade 11 that the tertiary carbocation is the most stable, followed by secondary and followed by primary. Okay, so this SN1 mechanism which proceeds via carbocation formation, which moves in the 2 steps. Okay, it favors the SN1 mechanism most, followed by secondary, followed by primary, followed by methyl group. This is the decreasing favor of the SN1 mechanism. Now if we move towards its graphical presentation, okay, again this is the energy of the reactant, the alkyl halide and the attacking nucleophile. Again, when they get the threshold amount of energy, okay, after getting the activation energy, intermediate cation is formed. Again it gets the required amount of activation energy, and finally it results into the product. Okay, so this is all about the SN1 and SN2 mechanism. Okay, so here remember that what is the trend followed: tertiary, secondary, primary and methyl. Decreasing favor of the SN1 mechanism, and here this opposite to this is, okay, tertiary, secondary, primary and methyl. It is increasing ease of the SN2 mechanism. Okay, now so wherever there is the stability of the carbocation, that favors the reaction via SN1 mechanism. Let's go through the comparison between the two. Okay, SN1, it is unimolecular reaction, as only the one molecule or one of the reactant, the concentration of one of the reactant is involved in the rate determining step, which is the slower step, which is the carbocation formation. In SN2, both the molecules are participating into the rate determining step. That's why it is bimolecular. Okay, and as only one of the reactant is involved, therefore it is the first order reaction. At both the molecules are involved, it is the second order kinetics. Okay, SN1 involves 2 step, it involves single step. Okay, SN1 involves 2 steps. In the first step, carbocation formation takes place, and in the second step it is attacked by the nucleophile, resulting into the product. In SN2, both the things, the leaving nucleophile and the coming nucleophile, both are happening at the same time. Rate of reaction depends only on the concentration of substrate only, as we have discussed. The rate of reaction depends upon the concentration of both the substrate and the nucleophile. Here in SN1, carbocation is formed as an intermediate part of the reaction. Okay, intermediate species. Here no carbocation forms, here forms the transition state. Okay, there is no partial bond formed with the carbon during this reaction. Okay, because in first step there is the complete breaking of the bond through heterolysis, resulting into the carbocation formation. Okay, here partial bonding happens because the leaving time and approaching time both are the same. The nucleophile attacks the carbocation from both the sides along backside attack dominates. See, it attacks the carbocation from both the sides. Okay, if it is exactly the inversion and the retention, if it is happening in equal amount, then it is racemic mixture, that means without the optical activity, because it gets cancelled. The inversion and retention are cancelled by each other. If it is not in exactly the same amount, then it depends which product dominates. Accordingly, the optical nature of the compound will be there. Okay. The attack of nucleophile takes place from the back side only, so there is always the inversion. If the optically active compound is there, there is always inversion. There is always the inversion of the nature of the optical activity. Here partially racemized product is formed, as I told you just now. If it is totally 50-50%, then it is optically inactive, and if it is not so, product will be accordingly only inverted products are formed. So this way we are done with the nucleophilic substitution reaction along with the its stereochemical aspects. Hope it's clear. Thank you children, have a great time.